Hello guys, welcome to today's tutorial, and today we just want to attempt to try and solve this question. So this question is from AC Power. So it says 120 volts RMS 60 Hz source supplies two loads in parallel as shown in problem form. Find the power factor of the parallel combination and calculate the value of the capacitance connected in parallel that will raise the power factor to unity. So in a nutshell, the concept being applied here is complex power. So let's just quickly go into solving the question. So for A, to determine the power factor of the parallel combination, we just use the law of conservation of AC power, which says that the total or average power, in this case complex power, will just be the sum of the individual loads. So, but we don't really have complex power here. We have been given something else. For let's say for instance for load 1, we can say load 1, we have actually been given an average power P, or we can just call it the apparent power or the real power if you want. This is actually equals to 24,000. And then we have also been given a power factor for load 1, which is just 0.8, and it is lagging. Then we know that the voltage source is equals to 120 volts RMS. Then the frequency is just equals to 60 Hz. So we know that we want to use the law of conservation of AC power and specifically complex power, but we don't really have the complex power here. So complex power in phasor form, and you mostly see this written as a bold-faced letter. It is just equals to the average power P, or you can call it the apparent power if you want, plus J Q, where Q is actually the reactive power. So with that said, we know what P is. Do we know what Q is? The answer is no. So mostly these formulas usually get a bit overwhelming. If you know your stuff very well, you can just plug them in. But if you know that you're not very good with memorizing formulas, I highly recommend you use the power triangle. So the power triangle simply looks like this. You have the real axis and the imaginary axis represented by P and Q, where S, the bold-faced letter, is just referring to the complex power. This will be your phi. So P is the real power or the average power if you like, and then Q is the reactive power, and then this is the complex power. So we have been given P to just be equals to 24,000 watts. So we also know what Q is. Oh, sorry, not Q, I mean phi. So phi is just this angle between the complex power and the real power. But then we can just obtain this phi by saying the power factor is equals to cosine phi. So with that said, we have been given the power factor. It is just 0.8 for load 1. So we can easily determine what phi, in this case it will be phi 1, to be cosine inverse of power factor. So that phi 1 is cosine inverse of 0.8. So you end up with phi 1 is just equals to, if you punch this on your calculator, cosine inverse 0.8, you get 36.87. 36.87. So you have your phi 1. You can just do some manipulation of this triangle. If you have this, you have the angle, you can easily find what Q is. So I mostly confuse this, so I like to use SOHCAHTOA. So if I have the adjacent and I am looking for the opposite, I know that I just have to use tan. So tan phi is equals to the opposite Q over the real power P. So that I can determine Q to just be, in this case it will just be tan phi. So that Q is 24K tan 36.87. I don't know if that's very clear, but yeah. So now if you punch this on your calculator, you realize that you just end up with 18,000, and the units for reactive power is just VAR, like this. So to now get the complex power, we realize that complex power is actually related to the apparent power, and in this case the apparent power is just the magnitude of the complex power. So maybe if you're using the power triangle, you even want to just use the magnitude of it, but no problem. We can simply resolve the complex power as follows. So we notice that the complex power, which is given as a broad face, is in fact just equals to P plus JQ. You know what P is, you know what Q is, we can just plug them in. So P, in this case, it's just going to be the value we are given, 24K, plus JQ is just 18K, and complex power is just denoted by voltage times amps. So this is your complex power 1. Now remember, the goal is to actually find the total complex power. This is what the question has asked for. Although they have not directly asked us for the complex power for the total loads, they have indirectly asked us by saying the power factor, but we know that power factor is in fact just related to the complex power. So we can easily now just find the complex power for loads 2. It's normally denoted by broad face letter. It will still be P2, I should have said 1 here, P2 plus JQ2. So when we look at loads 2, again we have been given just P2 to be equals to 40K watts, right? And then we have also been given a power factor of 0.95. So again, once you have just written down your data, if you are someone who is like me, I mostly mess up the formulas, so I just want to use the power triangle because it will tell me what's missing, what's not there, and all that I have. So this is fine. This is the real power P. This will be the reactive power Q. So now, with that said, we can easily just find this angle here because we have been given the real power to just be 40 watts. Now we can say cosine of phi which is just the power factor in this case, is equals to 0.95. So that we can say 5 is cosine inverse of 0.95. So 5, if you ask this on your calculator, you just get cosine inverse of 0.95, you get 18.19 degrees. Okay, it looks okay. Hopefully it's okay. So we now have, so we can work out what Q is from this using the triangle. I think it's the same thing as what we did in the previous example, because we just have the adjacent, we have the adjacent here, and then we also have the opposite like this. So we just need to use the tangent function. Tangent phi is just equals to, it's actually Thor, so the opposite Q, the adjacent P. So that hopefully you guys don't mix. This is actually the angle phi, and this is Q, the reactive power. So Q, the reactive power, is just P tan phi. So Q, P is just 40K. Then times the tangent, we just found the angle to be 18.19. So Q is equal to, if you punch this on your calculator, you just get the angle tangent times 40K 10 to the power 3. You get 13, it's a big number, 13,147.36, like that. Yes, so this is given in terms of VAR, voltage ampere reactive. So again, you can find your complex power for loads 2 as just being equals to PE2 plus JQ2. So we've been given P2 to be 40K plus JQ2 now will be, if you divide this by 1,000, you get 13.15K, and it is just voltage ampere. Okay, so we have the complex power for load 1 and the complex power for load 2. So what can we do with these two? We know that to find the total complex power, we just need to add. We can even use some primary algebra here. So we say S1, usually given as a boldface letter, is just what did we find there? It is 24K plus 18K voltage ampere. So it is 24K plus 18 and J18 and K. Then S2 is just what we are from finding there, 40K plus 13.15K. All this is in voltage ampere. So that the total complex power will be, you just need to add the two. You say 24 plus 40, you get 64 plus 18 plus 13.5, you get, this is in terms of K, that 1.5K, and it is in voltage ampere. So you now have your total complex power, but the question asked for the total power factor. So you need to find the relationship. Let me just open up a new page. So now recall something. Just like this. So you want to remember that power factor is just given as a ratio of the real power to the apparent power, and this is also the same as cosine phi, but this can also be written as cosine theta v minus theta I, where this is the phase angle for the voltage and theta I is the phase angle for the current. So now this is the apparent power, but apparent power usually given just as the way it is, S is the magnitude of the complex power given as a bold-faced letter. We have the complex power, and in this case, let's just say total, and this will be the total apparent power. So, do we know what the total real power is? We just need to come here. So, this column here represents the real power, and this is the reactive power. So the total real power is 64k. So we can say the total real power is 64k. Now we need to know what the magnitude of ST will be. So in this case, you just have to get the magnitude for this, and it's going to be the square root of all that. So square root, then we square 64 plus square 31.5. We just get, what do we get now? We want to say 64 squared plus 31.5 squared. You get 50, and you square it. Okay, you get now 71.33. Yeah, and this is just K voltage ampere. Yes, so you have everything. So you can say power factor is now just equals to 64 over 71.33. So if you say 64 divided by this answer, you just get 0.897. Now we notice that for some reason, because we are getting this ratio, the power factor usually is just dimensionless. So another way you can easily know if you have made a mistake or not is if in fact you just end up with a number which is bigger than 1. So the power factor ranges from 0 less than or equal to power factor less than or equal to 1. It can never be negative, it can never be greater than 1. If you find 50, then you have made a mistake. So because we have used up a lot of time, we are going to answer the second part of this question in the next video. Thank you and have a good day.